Today, we continue our analysis of the atom. If you recall where we were, we had accomplished our separation of variables, and we've been focusing primarily on this angular portion of the equation. Our goal for today is to determine the value of this constant A from the angular equation, which will then allow us to set that constant equal to the radial parts so that we can then also solve the radial equation and finally determine the allowed values of energy for the atom. So last time, we were focused on this equation, as we had said, and we had turned it around into the standard quantum purity test equation, telling us then that these functions y, which are known as the spherical harmonics, simply represent the pure states of the total angular momentum operator L squared. In our analysis of this equation, we began by looking at the simpler problem, first, of considering solutions to the LZ operator. What are the pure states of LZ? We used that sort of as a warm-up to establish our thinking, and that went quite well. We made a point that, in fact, we weren't wasting our time by first focusing on LZ, because LZ and L squared are compatible operators. Therefore, we can ensure that when we find we can find a set of states that will be simultaneously pure with LZ and L squared. So finding the pure states of LZ is definitely a very good first step towards finding the pure states of L squared. And that argument was based on the fact of this commutator being 0. This does raise an interesting question, though, about the other operators and how their commutators with L squared would look. So I'd like to think about that a little bit with you. And I'd like to make a note on a very powerful technique known as cyclic permutation of variables. So to begin, our logic is the following. L squared represents an actual, physical operator, the total angular momentum squared of my physical system. And LZ is the angular momentum about a particular axis. Now, whether we call this axis Z or something else should not change the underlying physics. The key to this, then, is that when we have our original coordinate system, x, y, z, our main physics shouldn't change. So if I were simply to relabel these axes, I should come to also correct conclusions. The physics should not depend on the axes. And in particular, if I happen to call this axis, which is vertical, which is some physical direction in space, if instead of calling it z, I might have chosen to call it x. And if I were to make that choice, so this is z, I'm going to change the name of this axis here to x, I would then still find a valid equation. Now, if I label this axis x, I have to be careful to label the other two axes y and z. And when I do this, I must respect one key fact. And that is the fact that I must always produce a right-handed coordinate system. Because none of our physical equations really necessarily care about the right-handedness of my coordinate system and how I label that system, except, of course, for the cross product. And the cross product is occurring throughout the theory that we've been developing because it is inherent in the definition of the angular momentum. Therefore, when I make my relabeling, if I want to pick an appropriate new labeling, I have to maintain a right-handed coordinate system. So it will not simply be arbitrary which one I call y and which one I call z for my other two axes. So let's decide sort of where these go. Now, it will turn out, and if we look at this carefully, if I make this one y and this one z, I will indeed have a right-handed coordinate system. Because if I look at the new x-axis and I do a cross product with the new y-axis, in fact, it will be aligned with the new z-axis. So this then is a valid relabeling of my variables. And if I relabel my variables this way, just changing my coordinate system, then LZ in this equation would become my LX, my L squared, which is Lx squared plus Ly squared plus Lz squared, will simply become the same sum, but in a different order. It would become Ly squared plus Lz squared plus Lx squared, but that equals the same thing. So the translation of this statement into my new coordinate system tells me, in fact, that this commutator here also must be 0. And I can carry out the same logic again. I could ask what will happen if I commute L squared instead of with Lx with Ly. And now I would have to find yet a new labeling of my axes. Now I would be calling this vertical axis the y-axis. And in doing so, I can find an appropriate label of x and z for these other two axes. And if we choose them this way, the z becomes x and the y becomes z, we again will have a right-handed coordinate system, because this x direction, right, this new x direction crossed with this new y direction indeed gives me my new z direction. So once again, this commutator here will also be 0. So we learned two things. First, we've learned that all of the components of the angular momentum operator actually commute with L squared. And this is ultimately a very sensible thing, because after all, L squared treats all directions in space equally. It's an equal combination of x squared, y squared, and LZ squared. And so it shouldn't depend upon any rotations. And these angular momentum operators, what they do is, in essence, implement rotations. So it's eminently reasonable, in fact, that all of those components should commute with something like L squared, which doesn't depend upon any particular direction in space. That's the first key lesson. The next key lesson is this fact that we can take any of our equations and simply relabel our axes to generate another valid equation. And there's a nice pattern in terms of how this mapping occurs. If you look at the first mapping that I made, what happened was the x-axis, right, got relabeled as the y-axis. And then the y-axis got relabeled as the x-axis got relabeled to the y-axis. And then the y-axis got moved over and relabeled as the z-axis, and then the z-axis got relabeled as the x-axis. And you'll notice there's a pattern where I keep moving forward. The z-axis, though, wrapped back around to the beginning, to the x-axis. So it makes kind of a cycle like this. And so this kind of relabeling of your axes is called a cyclic permutation. Now, if we carried out this operation and it gave us a valid relabeling, as it did, I can carry out exactly the same type of operation, and that perfectly captures the second labeling, because in the second labeling, the new axis went to the y-axis, the new y-axis went to the new z-axis, and the new z-axis went back around to the x-axis. So you can think about it in one of two ways. You can think about this second new relabeling as either moving two steps forward in the chain, where x goes to z and y goes to x and z goes to y, or because there's only 3 items in this cycle, you can think of that as going backwards, where x now goes to z, as we see in this case, x finally went to z, and then y, going backwards, should go to x, and it does. It goes back to x through z, and then finally the x, if I move that one, if I go start at the z and I move that one backwards, it would become y, which is what I got in the second of the relabelings. So you can generate these equations very quickly from those cyclic permutations. And that closes my little note. It's very handy, though, because as we will see in today's lecture, many times we can generate many results very quickly, save ourselves a lot of time. Very good. Now, we had gone a little bit further. Once we decided that we could seek simultaneous solutions of the total angular momentum and the z component of the angular momentum, we wrote down names for the corresponding equations, and we also did a little bit of a dimensional analysis. So this total angular momentum squared operator should have units of angular momentum squared. It turns out that h bar has units of angular momentum. So another way of writing the eigenvalue, or the pure state value for this operator, is simply to call that pure state value h bar squared times some dimensionless constant lambda squared. So lambda, therefore, represents the magnitude of the total angular momentum vector, measured just in units of h bar. Likewise, for the z component of the angular momentum, we labeled that as some dimensionless constant, which we called m, times the h bar, which would have my units of angular momentum. And then this then defines for me a set of states that are pure with respect to both L squared and LZ. Now, when we have such a set of states, it's useful to have some notation so I know at any instant in time which state I'm talking about. And the best way to label these states is by their properties, namely their pure state values. So we are labeling these functions y now by their lambda value and by their m value. So they're all written as y sub lambda m. That cleans up our notation a little bit. We then further explored some of the key properties of these eigenvalues. Since lambda represents, in dimensionless units, the magnitude of the total angular momentum, it's clear that it must be larger than the magnitude of just the z component of the angular momentum, which is what m measures for us. And we had also gone through the effort of actually solving for the pure states of the LZ operator. And by imposing the finiteness of the sphere and the periodic boundary conditions, what we learned from that analysis is that, in fact, this value m had to be an integer. So we got a discrete set of values for m, and m always must have an integer value, which will play a key role at the end of our analysis in terms of telling us what the actual allowed L squared pure state values are going to be, and therefore what we need to solve for the radial equation. We then began in earnest our analysis of really finding what these L squared pure state values could be. And we began by paralleling what was so successful with the simple harmonic oscillator. We factored our L squared operator into a product. Since this is really a sum of quadratic operators, we factored it into a product of two linear operators, which we defined as L plus and L minus, with this Lx equals plus or minus I Ly, with this notation that helps us remember the formula. But as we're going to see, that plus and minus actually plays a much deeper role than just the sign in this particular formula. But in any event, by making this factorization, which needed a slight correction in terms of this commutator, we were able to write down the total angular momentum squared operator in this much more convenient notation that parallels closely what works so well with the harmonic oscillator. So our main goals for today are really twofold. We have a smaller goal, which is to determine the value of this commutator, which, as you can imagine, is going to be a very important type of a commutator in our theory. And we also need it to complete this formula, and thereby to complete our analysis of the allowed eigenvalues of L squared. And the larger term goal actually is that, to determine what are these allowed values of this parameter A. A final note before we begin our analysis, which will begin with determining this commutator, is a note on notation. This commutator, it turns out, is going to be pretty messy, and there's going to be a lot of writing here on the screen and also in your notes. And when we're doing all of that writing, it's going to slow things down quite a bit if we insist on writing all of our operator hats. As you go on in physics, what you're going to learn is that we use these notations originally so that it's very clear to us what our various objects are. But after a while, and after we gain experience, and you've been gaining experience throughout this course, we begin to pick up the skill of actually knowing from context which quantities are operators and which are not operators. So I'm going to take advantage of that a little bit today to save our writing and to make it a little bit more quick and efficient, right? So the operators that we will be working with today are the components of the angular momentum operator, the components of the position operator, and the components of the momentum operators. And I think from context, we know that all of these things in quantum mechanics would be represented by operators. So I'm going to take all of these hats, right, and I'm going to remove them in today's lecture. And we're just going to write down the actual variables themselves just to save on some of the writing. It should be clear, though, that there are other objects that will appear today, and I believe this is a complete list. If it's not, I still think you will be able to tell from context, but these are things that are clearly not operators, and I hope you will keep that in mind. You know, the square root of minus 1i is not an operator, h bar is a constant, y are these functions that we're solving for, theta and phi are just my angular coordinates, lambda and m are just these dimensionless parameters that characterize the magnitude of the total angular momentum and the z component of the angular momentum. And there will be two other integers that appear in today's theory, lowercase l and lowercase k. And all of these will be clearly not operators. If you're wondering what's an operator, this is an exhaustive list of the operators that we will be working with today. And with that said, then, I think we're ready really to begin to focus on today's main task, at least the initial task, which is to compute this commutator.